Course 3, Investigation 11. On this investigation, we are actually looking at nonlinear functions, things that go on basically a curve rather than a straight line. So, for instance, suppose we took photographs at half-second intervals of a ball that is pushed off of a high ledge. The result might look something like this. And you can see at 0 seconds, we have a certain height, half, 1 second, 1.5, and then we're to the ground. So the ball does not follow a straight line path to the ground. This path is curved. In general, we call this type of curve a parabola. We can write a function that models the height of the ball at any given time. The graph of the function we would consider a parabola. So we're going to actually plug this into a table to say what are the different values that we have. So here we go. In this first one, use the diagram above to chart the height of the ball at each instant of time. So let's use that. Let's start from where it starts at the top of the building. So at 0 seconds, we have, it looks like we're in feet, so we are at 48 feet. So 0 seconds and 48 feet. All right, let's continue. Half a second would be next, and it looks like we are going by fours here. So this would be at 44. So half a second, we're at 44. And then at 1 second, and then we'll talk about 1.5. All right, so at 1 second, it looks like it's then at 32. And then lastly, at 1.5, we are at 12 feet. Okay, so based on the diagram that we have above, this is what we would say is our table of the information. Now, we also have this equation that we could use to describe the situation here. Well, let's plug in these time values or x values to see what we get. So, y being our height, I can plug in 0 seconds, so 16 times 0 squared plus 48. And that 0 squared kind of cancels out that negative 16. We get just y equals 48. All right. And then we can substitute 1 in here instead of 0. Well, that just gives us negative 16 plus 48. Well, oops, I missed one. I should have had 1/2 here. Sorry about that. Let's try that again. Okay, 1/2 squared. Well, 1/2 squared is 1/4, so I have negative 16 times 1/4 plus 48. That means that I have negative 16 times 1/4. Well, that's negative 4 plus 48, which is 44 feet. Looking familiar to what we had earlier. All right, now let's try this again with 1 second. We get negative 16 plus 48, which gives me 32 feet. And as you can imagine, and you can check this out, when I put 1.5 seconds in there, I am going to get 12 feet. These are exactly the same because this equation does actually show that situation that we had above in the diagram. So we see that the graph of the height of the falling ball versus the time are the same, okay, which it should be, considering that equation actually shows the parabola. Notice that the function has an x squared term in it. We haven't had functions so far with x squared terms in it. We call this type of function a quadratic function. So what we've had before with just x in there, that would be considered a linear function, whereas x squared is a quadratic. So the quadratic function models the height y of the ball at any time x. So just to kind of say a little bit more about what this term quadratic mean, it comes, even though it has quad, kind of like what we think of like a quarter. So, you know, splitting into 4, or maybe we think of maybe it should have an exponent of 4. It actually comes from a Greek word meaning square. So it does actually make sense in this situation, especially since a lot of our math does come from the Greek, a lot of the words that we use in math. So the quadratic function models this height and time relationship between the two. So describe this graph of y equals negative 16x squared plus 48 For x values less than 0, in the situation of the falling ball, why are we only concerned about the portion of the graph in the first quadrant? Basically, why do we care of only that solid line rather than these dotted lines? Well, when we think about this, if I were to actually put values on x being negative, so let's say I have x being -2 right here, that would mean I would have -2 seconds. And honestly, that doesn't make any sense in real life. We can't have -2 seconds. So we only want those x values that are positive, because that would mean positive time values. That makes sense. But also, why don't we care then about like this lower portion right here? So why don't we care about this part right there? Well, if we think about those y values that are negative, let's say -10, that would mean that we have -10 feet. Just like the seconds, we don't typically measure things in negative feet. What that would mean is that that ball has actually continued through the earth and is now -10 feet into the earth. We don't talk about that. So we really only care in real situations about positive time and positive feet. So think about logically why we choose some of these pieces. So the quadratic function, -16x² plus 48, comes from the study of physics and the force of gravity. When we only consider the force of gravity and ignore other forces such as wind and friction, the height of any falling object on the earth can be described by this quadratic equation. So friction and wind do change it a little bit in real life, but in general it does show this shape. So the graph function on the previous page, we just consider them nonlinear. Yes, we can have fancy name like quadratic or parabola, but truly they're just nonlinear. Their points do not lie on a straight line. The height of the ball is not subject to a constant rate of change. Because as you can see from up here, even though we were going by the same increment of seconds, half a second between each, we were not falling at a constant rate. If that were true, we would see -4 here and then another -4 and -4. That's not true. So this is definitely not linear because we do not have that constant rate between our values here. So the ball moves faster as time goes by. It speeds up a little bit. So in the first half second, the ball falls 4 feet, but then the next one, it falls 8 feet, just like I was showing above. It doesn't have a constant speed. So let's go ahead and look at a different situation here. So it says Leslie held a softball 5 feet above the ground, and she threw it straight up at 32 feet per second. She has studied physics and predicted that, considering only gravity, the height h in feet of the ball at t seconds could be described by this function. -16t² plus 32t plus 5 gives us the height. And you can kind of start to visualize what this looks like. She's throwing it up in the air, it goes up, 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 and then comes back down. Okay, and so we see a little bit of information about this parabola. The maximum height came after 1 second of it being in the air, and it went up to 21 feet. And then it also tells us that at 2 seconds, the ball hits the ground just after that. Okay, you can imagine this coming down just a little bit after 2 seconds. So we would say it hits the ground just after that. So let's answer some questions about this. Complete the table to find the height of the ball at 0, 1, and 2 seconds. So there's a lot of different ways that we can do this, and in Algebra 1 you'll learn many of them. But for right now, let's just use that equation. I'll write it down again. H equals -16t² plus 32t plus 5. And what we can do here is just plug in 0, 1, and 2 into this equation for t. So let's do that. And we're going to say h equals -16 times 0² plus 32 times 0 plus 5. And so those all cancel out and we just get 5. All right, then let's plug in 1. -16 times 1² plus 32 times 1 plus 5. Well, a little bit more work here, but negative 16 plus 32 plus 5. This part just gives me a positive 16 plus 5 is 21, and that's where we get our maximum point, actually. And then our last one at 2 seconds. Negative 16 times 2 squared plus 32 times 2 plus 5. Well, that gives us negative 16 times 4 is a negative 64 plus 64 plus 5. So those first two cancel out and we just get 5 again. Parabolas do have quite a bit of symmetry here, so it's not surprising that we see 5 feet as our height twice in this table. So number 4 says plot the points T and H. What is the maximum height of the ball? When does it reach the ground? Or when does it reach this height? Approximately when does the ball hit the ground? So you can go ahead and plot this for yourself. I'm not going to show it again because we do have it up here. And so you can see our beginning point at 0.5, our top maximum, and then at 2 seconds. And then just like we said earlier, if this were to continue, I would approximate it at like 2.2 seconds. Something like that would make sense. All right, so just a couple more things here. So this is a good thing to think about and write down, but for activities 1 and 2, describe the difference between the paths that the balls follow and the graphs of height versus time. So think about the two different parabolas that we actually saw and how they are similar and how they are different. If I were going to write them down, and of course pause this before you listen to what I say, but one of the things that really makes a difference between the two parabolas, one of them, we start at a maximum height and we just see the decrease, whereas the second one, we see our full parabola increase and decrease. So very different, even though they have similar characteristics because they're both curved, both a parabola. So to talk about one more vocab term here, that's the vertex. So the graph of every quadratic function is a parabola with a vertex that indicates the maximum or minimum value of a function. So far we've only seen maximums, things that look like this. We have a maximum and we call that a vertex. But other parabolas can be upside down like this, where the minimum is also considered the vertex. Vertex in its basic form does actually mean that we have a change in direction, basically. We are increasing, like this one, increasing and then decreasing, or decreasing and then increasing. We are changing directions. So it's that change of direction is our vertex. Okay, so our last activity here, we are looking at maximization. So we have 20 yards of fencing here, and we need to enclose a rectangular plot of land for this garden, only using 20 yards of fencing. So this person wonders what the rectangle's dimensions would have to be to contain a maximum area only using these 20 yards of fencing. So to solve this puzzle, they drew a rectangle and named one side X. All right, we can see that right there. Here's my X. I don't know what the value of that side length is. And then since half of the perimeter of the rectangle is 10 yards, okay, we're going to have to split that up somehow. He reasoned that the other side length must be half of that, so 10 minus our X value. So using X and X minus 10 as the dimensions of the rectangle, we can write an equation. So of course we use our area formula. X times 10 minus X is what we're going to get. So we end up with this area formula. And as we can see, this is actually quadratic. And we know that because of this x squared. That x squared tells me that this is a quadratic. So, because that highest power is 2, we do actually end up with a quadratic that is a parabola. So, if we want to find what the maximum area is, we could find the maximum of this parabola. So first of all, we can start out with what x values make sense in this situation, remembering that we can only have 20 yards of fencing. So write an inequality to show the values x can take, and then use the area function to complete the table, and find the areas of the rectangles with different lengths. So you can see a couple of these done already. If we had a rectangle that's 2 by 8. 2 by 8 would give us a perimeter of 20, and that gives me an area of 16. Okay, what if x was 3? Well, if x was 3, that would make the other side 7, and we would get an area of 21. So that's good, we're getting higher. What if our x value was 4? Well, that would mean that this other side length must be 6. So our area must be 24. Notice that, once again, all of these side lengths, 2 and 8, 3 and 7, 4 and 6, add up to half of the perimeter, so 10. So if I have 5 by 5, that's going to give me an area of 25. And then we kind of start over. 6 and 4 would give me now an area of 24 again. 7 and 3 would give me an area of 21, and 8 and 2 would give me an area of 16. So we have all of our possible whole number areas here with those possible perimeters. And it says graph the points X and A from your chart, indicate the vertex on your graph. I'm just going to do a quick sketch of what this is going to look like so that we can visualize what is happening here. So here we go. All right, so here's 10. And then I'm going to skip some numbers here. 5, 10, 15, 20, 25. So this is my area on the y-axis since it's dependent on the perimeter, and x values are plotted on the x-axis. So we start with, we can just start with our lowest one. So x as 2, and so my area is 16. We would have a plot right about there. And then 3 goes to 21. 4 goes to 24, just below that. 5 goes to 25. 6 goes back to 24. 7 to this 21. And 8 goes to 16 again. So we have this parabola, and now I'm just going to extend it a little bit to show that yes, we could have some other possibilities here that are decimal numbers. We're plotting just those whole numbers. And we can see that our maximum here, our vertex at 5 as our x and 25 as my area, would end up being the maximum point. This would be using all of those 20 yards of fencing and getting the greatest number of area for my garden. So in this case, to maximize the garden, I would use a 5 by 5 plot in order to get the biggest garden. So we can use parabolas for a lot of different things to visualize things in the air, but then also to maximize our results. Pretty cool. All right, so this was investigation 11. And I hope this helps with your homework and for studying.